Right. So this is what I'm going to speak about briefly. What exactly is radioactivity or ionizing radiation? A little bit about what happens in a uranium mine and what happens in a reactor, and about the health, of course. A little bit about regulation and waste, and weapons briefly. So firstly, what is ionizing radiation? So if you remember your high school chemistry, you've got your periodic table, and on it you have all these elements. So every element has protons, which are positively charged, and electrons, which are negatively charged, and they have the same number of each of those, so every atom is neutral. The protons have mass, the electrons kind of flit around and they don't have mass. There are also neutrons, which also have mass, and they're neutrally charged, so the whole atom doesn't have charge. The little number that goes beside each element is either the atomic mass or atomic number. Anyway, it's the addition between the protons and the neutrons, so it's how much mass every atom has. So uranium-238 has, if you add up the protons and the neutrons, you get 238. So some atoms have isotopes, which is they're exactly the same element, except they have different numbers of neutrons, so the little number changes. So uranium isotopes are 238, 235, and 234, and they differ in the amount of neutrons they have. Most of these are stable, but some of these isotopes of some of the elements are what we call unstable, and we call these radioactive. And what it means is they have this propensity to shoot out little bits of themselves at high speed. And when they do that, or they shoot out little high-energy photons, but in so doing, they actually become a different element, which is called a decay product. And if that one is radioactive, it shoots off its little particle and becomes something else. And it will keep doing this down what we call the decay chain, if each of them are radioactive, until they reach something that's stable. So this is an example of uranium-238. So if you look along the left, you'll see everything on that decay chain actually is radioactive until it gets down to lead-206, which it's stable. So every atom of U-238 has to go down that chain and become an atom of lead-206. I want to point out one of them, about the 7th or 8th one down, is radon, which we've talked about, which is a gas. And it's a potent lung carcinogen. On the right are the bars showing the half-life, and what that means is how long it takes for half of whatever little pile of uranium-238 you have to disappear and become thorium-234. Some half-lives of these are very long, like U-238, it's 4.5 billion years. So it's very slow to kind of shoot off its particles, but it's around a very long time. Some of them are very short, in microseconds. And it takes about 10 half-lives for the whole pile of it to become the next one down. So this is Alexander Litvinenko, who was a Russian spy. He ended up living in the UK, and in 2006, he was poisoned with polonium-214, which is a 210? Sorry, 210. That's right, because it's further down, and it has a little bit of a longer half-life. So it's very, very, very toxic in very, very, very small amounts. And he was considered to be the first person to die from nuclear terrorism. Interestingly, since then, Yasser Arafat, there was talk of him having been poisoned also by polonium-210. They exhumed his body a few years ago and eventually decided that he wasn't, but of course we never really know what happens. This is a picture of him 2 weeks later, just before he died of acute radiation sickness. So uranium, which is what we've been talking about. So generally speaking, in rock, there is mostly uranium-238 with a little bit of 235. Uranium mining is like any mine, big hole in the ground. They take out the rock, they crush it, they extract the uranium out of it. It's all a very dirty process, which is called yellow cake. And then they move that to a refining place. In Canada, most of our uranium, of course, comes from northern Saskatchewan, a little bit in Ontario and other places. All of it goes to Blind River, and then it goes to Port Hope, which is just east of Toronto, where it's refined, as Ian had mentioned yesterday, into uranium hexafluoride, What's going to the US needs to be enriched because their reactors like more 235, and they have this process they call enrichment, which means they kind of filter out the 238, which is a little bit of a bigger molecule, and they get mostly well, not mostly, they increase the percentage of 235, which is what they use in their reactors. In Canada, our CANDU reactors use, we don't use enriched uranium. And just as an aside, because it's part of a health issue, they end up with extra 238. And somebody yesterday, I think it was Gordon Edwards, was talking about the depleted uranium, the extra. So this is very dense. And what they do with it, because it's a waste product in the States, is they put it on the outside of bullets, they put it on the outside of tanks, and they use it. They have used it in various parts of the world. There's a lot of concern. Oh, and when it on impact, it combusts and makes a very fine mist, which when you inhale it goes into your lungs and is so tiny that it will go into your system and deposit in your tissues. So that's uranium-238. As I had said, it has to go down that decay chain. Every atom of it has to go down that. And when it does that in your body, it wreaks havoc because it's throwing off a couple of protons and a couple of neutrons. Those ones that have what we call alpha or internal emission, which I'm going to talk about in a minute, and they will damage adjacent tissue. So there is also a lot of concern about soldiers coming home from the Balkans, Gulf, Iraq, and Afghanistan, that they are coming home with illnesses in higher rates than other people of their age, particularly things like lymphoma. That is thought to be due to depleted uranium exposure. And that's not to mention all those people living in those war-torn areas where the children are playing on the ground with all depleted uranium dust and in the burnt-out tanks. Nobody's really studied it, but there are anecdotal stories of high rates of very bizarre birth defects, cancers, miscarriages, infertility in people that live in these war zones. So uranium miners, as Eric and Isabelle talked about the public health review in Quebec that was done, the biggest problem has been historically in miners, high rates of lung cancer due to the radon, because in the rock down in the mine, every atom of U-238 has to go down that chain. Radon is one of those things. It builds up underground and they inhale it. It's the most potent, it's a potent lung carcinogen and the most common cause of lung cancer after smoking. They also have other problems with the silica that causes silicosis, and uranium is also a kidney toxin, so they also can have kidney damage, which was actually shown in one of the studies that Eric talked about. This is in people living near uranium mines, a little bit of higher rates in the women of kidney disease. In Elliott Lake in 1976, there was so much concern. The miners had a strike, and that prompted the Ham Commission, which set up some guidelines in mining, but also particularly in uranium mining, because not only are the tailings toxic, but they are radioactive. And as people have talked about a lot, and they'll talk a lot tomorrow about, that it always ends up being mining, and particularly uranium mining on Aboriginal land, which is all a huge other issue, which we'll address mostly tomorrow. So this is just a picture of tailings ponds. What they do is they put water over all this extra rock that's still got lots of uranium in it. They put the water on it to keep the radon down, which probably doesn't do a very good job. They put a little bit of a wall around it in an effort to prevent it leaking out into the groundwater, into the soil, and invariably it gets into the air, water, and soil. So what happens inside a reactor? Well, basically you've got fuel bundles with uranium in them. They get bombarded with neutrons, and that causes the atoms to split. It causes what we call fission, and it's a self-sustaining process. Now, if there's no control on it, it causes a massive blast, because every time an atom splits, it gives off heat. And so you get a massive blast, and that's what basically a nuclear bomb is. But if you do it in a controlled manner, which is what happens inside a reactor, you have these moderating substances and neutron-absorbing substances, and you're constantly putting water around it to control the heat. You get that heat, which causes water to boil, which turns turbines, which makes electricity, and that's how it works. Now, you can see how if there's a problem with the control, it's going to overheat, then you get massive blasts, meltdowns, etc., which is what happens in these major and minor accidents. We probably don't hear much about the minor accidents. Now, the fuel rods are contain what's are alpha emitters, basically the uranium. And alpha is when it throws off 2 protons, 2 neutrons. Now, these are called internal emitters, alpha and beta emitters, because they throw off these little particles, but they don't go very far. So in fact, they won't penetrate your skin. You can actually hold a fuel bundle. But the fuel rods that come out the other end have undergone a lot of fission. You have a lot of fission products. They're all radioactive and very toxic with gamma radiation, which is a different kind of radiation. It's a little bit like X-rays, where it will actually penetrate, it goes through you. In so doing, it will damage the tissue on the way in. So you can't go near spent fuel bundles. And in fact, they contain all sorts of uranium fragments, a lot of made products that aren't natural. One of them is plutonium, which some places will extract the plutonium out of the reactor fuel and use it as the spent fuel to use in other reactors. We don't do that. But the key here is that it's what's used in bombs. And this is the link between the nuclear energy industry and nuclear weapons. Then these spent fuel rods have to be cooled. They put them in kind of swimming pool-like things, and they run water around them. They have to do that for about 7 to 10 years so they can reduce the temperature enough to be able to handle them. We put them in dry storage, and nobody worldwide has ever figured out what to do with them after that. So this is an example of the lung. It's a bit of lung tissue from a chimpanzee, and that in the middle is a particle of plutonium. So the little trajectories coming out of it are the protons and neutrons it's shooting off, because it's an alpha emitter. And you can see that it will damage the cells around it. And if it damages the nucleus of the cells around it, it can cause DNA damage. So gamma, as I said, is penetrating. That will damage tissue as it goes through. Then there's alpha and beta, which I described as non-penetrating. These are called internal emitters because if you ingest or inhale them, they will lodge in your tissues, and they will continue to throw off those little particles and damage the cells around them. Polonium, U-238, and radon are all alpha emitters. Strontium, cesium, iodine, as well as tritium, they're all beta emitters. They're all internal emitters, and they cause damage inside you, and you can't remove them from your tissues. So when they're in there, they have to go down. Every atom of what you have there has to go down its whole chain in order to arrive at something stable. And there's no way you can stop that. So the health effects, like anything, acute health effects are pretty easy to look at and measure because they happen right away and you can observe them. What's much more insidious are the low level of radiation that we're all exposed to. And it is causing DNA damage. Now, we know DNA damage causes cancer, it causes birth defects, causes infertility, miscarriage, it causes immune dysfunction and diabetes, it speeds up atherosclerosis. And if it affects sperm and egg, it will cause inheritable disease, which may not show up for several generations. The most susceptible organs are the fast reproducing organs, the blood, the bone marrow, gonads, embryonic tissues, fetal tissues, your GI tract, and growing bones and cartilage in children. Particularly radiosensitive cancers are the thyroid and the bone marrow, which is mostly leukemia. Children are more vulnerable because they're growing fast. Women are more vulnerable. It's not exactly understood why, other than that the breasts and ovaries possibly are more sensitive as girls become pubertal and exposed to radiation. And remember, these processes for the internal emitters are continuous and irreversible. So background radiation generally averaged out is about 2.4 millisieverts per year. A millisievert is just a measurement of radiation, mostly from gamma rays from the sun and radon that's mostly emanating from the ground. Added to it is the emissions from nuclear power stations, above ground weapons testing in the past, all the accidents, and medical procedures, mostly CT scans. Okay. So we are allowed, and these numbers are totally arbitrary, and they've been going down and down and down over the decades. Right now in Canada, we're allowed 1.0 millisieverts per year. Interestingly, we allow way more than that for nuclear workers who work in the plants. Maximum of 50 millisieverts a year and 100 over 5 years, which results in way higher rates of cancer per 100 workers over a 40-year career. Normally, we accept 1 in 10,000 to 1 in a million. This is 3 in 100. So safety, remember, it's cumulative over time. What is an acceptable risk is really, in Canada, it seems to be decided by the CNSC, which is a very pro-nuclear organization. All we have is studies, which Ian is going to talk to us about. But they have their innate limitations, and really, if you want to be able to look at a study, you have to know a little epidemiology, and you have to be able to really assess. You have to look at it yourself and figure out the limitations and what it really means. They go with the ALERA principle, which is as low as reasonably achievable. In other words, that we try and reduce the exposure if possible. Just a word about the LNT, which is a linear no threshold hypothesis, which most regulatory agencies worldwide agree with, which is that all radiation is harmful. As the dose goes up, the harm goes up in a linear fashion. If you look at Ian's website, he has lots of examples of studies that show harm under 100 millisieverts, which even the CNSC disputes, because they say, well, under 100, there's no evidence that it's harmful, which clearly is not true. Just a word about nuclear waste. Nobody's figured out what to do with it. There's a lot of controversy in Ontario right now. People, small towns wanting jobs who are offering themselves up. They want to dig a hole in the Canadian Shield, I don't know how deep it is, a kilometer, put it down there, and then cross their fingers that nothing happens to it. This is right next to Lake Huron, which is one of the Great Lakes, the largest freshwater body in the world that may become contaminated. There's also the issue of transporting all this toxic waste to the site. And weapons proliferation, I don't need to say any more about. No meaningful medical response to a nuclear war. And depleted uranium, I've already mentioned. And so this is my summary here. And I'm going to pass the mic over to Ian.
I'm going to be talking about a rather vexed topic, and that is childhood leukemia near nuclear power facilities. This is a long, long history. It's been going at least for 30 years. This is not new. When I was living in the UK back in the 1980s, there was a big, big scandal about increased childhood leukemias near Sellafield, which is a huge nuclear reprocessing plant on the northeast coast of England. And can we get the lighting ready? Oh, good. Just leave it, okay? And what happened was that they couldn't explain a village called Seascale within 4 kilometers of Sellafield. And all the nuclear bods, then it was the National Radiological Protection Board, said there's no way that this could be due to the radioactivity releases from Sellafield. Those models don't show this. We can't explain why there should be such big increases. But at the time, this is like 1985, 86 in England, there was nobody around to figure out what was going on. But now there is, and that's the big difference. I was around in England at the time, and I couldn't figure out why this was going on. And I've spent the last 20, 30 years trying to figure it out, and I've figured it out. And I'm here to tell you what the answer is. Essentially, back in the 1980s, the whole debate fizzled out. And there it rested until 2008, when there was a big report from Germany. It was called the KIK report. KIK is just an acronym. It means Kinderkrebs in der Umgebung von Kernkraftwerken. You got that? but it's important. Basically, what happened is that the German government had a number of anecdotal reports given to it by a German initiative group, a citizen initiativen group in Germany. And so the German government said, we're fed up with this. We're going to show you, we're going to do an study, an epidemiological study, and we're going to prove once and for all that there's nothing to worry about. This is just a pile of nonsense. We're going to disprove this for you. So they commissioned a very good team of epidemiologists in Mainz University in Germany, Maria Blattner, one of the world's top epidemiologists, and said, look, here's a pile of money. Take your team and spend 3 or 4 years setting up the mother and father of all epidemiological studies, and we're going to show, boom, there's nothing there. Except it was exactly the opposite. They were stunned to find out that there were big increases in childhood leukemias near all German nuclear power stations. And I'm not talking about 10, 20% increases. I'm talking about 120% increases. The German government didn't know what the heck to do. The Environment Department sat on the report for 9 months because it just couldn't face telling the German government the bad news. But the German government had said, look, what's happening with this, and would you please report by at least by the end of 2008. On December the 31st, at midnight, they put it on the website. I'm not kidding you. Nobody found out about it until January, about 30 days later, when IPPNW, you've probably heard of them, in Germany, stumbled upon this report. Up till then, it was absolute silence from everybody in the German government. But when it came out, it was just astonishing. This showed a 120% increase in childhood leukemias, which in terms of those who know about relative risk means a relative risk of 2.2. Now, this is very serious stuff. I mean, if this was, say, chemicals or genetically modified food, they would stop it immediately. But no, this was nuclear and different rules applying. And there was also a 60% increase in embryonal cancers. Now, what does that mean? It means that babies were being born with solid cancers. They had never seen that before. So, well, it had never been linked with proximity to reactors. However, the German government said, yes, we have to accept it. And we've double-checked the methodology, and these results are definite. This is a graph from the study which shows that if you this is 50 kilometers, 25 kilometers, 10 kilometers, 5 kilometers. As the closer you get to the reactor, the risks increase exponentially. So that's the key thing. The closer you get, the risks really, really increase. And within 5 clicks, the risks are very high indeed. And indeed, I have made recommendations in Toronto, and also I'm going to make it up in Pembroke in Ontario, that people, mothers and pregnant women should really move away from within 5 kilometers of plants putting out large amounts of radionuclides, in particular tritium. I'll come back in a minute. Now, you may say, well, Ian, that's all very fine and dandy with KIC, but do other studies show that? Well, yes, they do. There were 2 other studies which I was astonished to find. First of all, Laurier et al. In 2008, and Laurier and his colleagues in 1999. They actually looked at the issue of childhood leukemias and nuclear facilities. And bingo, it turns out that there's about 60 studies worldwide. Now, because what I've done is I've added the 26 multi-site studies and 36 and 14 single and multi-site studies. And when you merge them together, you get over 60 studies. The very large majority, 40 out of those 60 studies, show increases. That doesn't mean the others don't show the increase, it's just that they didn't find them. Mainly because many of these studies are small and you can't really tell anything with small studies. But as a result of KIC study in 2008, three other European governments set up their own studies. And I'm showing you the results here. And what you can do is you can pool the data together, and Alfred Korbland and myself, we did that. And what we can see here from this, if this works, is that we have a 37% increase in childhood leukemias within under 5 years old, within 5 kilometers. And that is statistically very significant. We've got a p-value here down at the bottom right hand. Sorry?
Say that conclusion again, 37%.
Increase in childhood leukemias throughout all of those 4 studies when they're pulled together. Now, interestingly, all of the studies show roughly that. In Germany, it's 1.4, and GP is 1.3, Switzerland, it's 1.4, and France, it's 1.37. Now, you may say, well, hang on, why is Germany slightly different? Well, this is looking just at, how would I put it, the data from data banks. This is not a case control study. The KIC study was a case control study. You get different results depending on how you measure it. Now, you may say, hang on, how can that work? It's because epidemiological studies are not an exact science. In fact, you find out it's better to do a case control study, but few countries actually do them. Germany did it and found, bingo, big increases. But if you use the old-fashioned way, which is very cheap, you just look at data tables, you come up with these results. All 4 countries had exactly the same results looking at all of their reactors. So the French reactors, the Swiss reactors, the British reactors, and the German reactors, when you study them all, you get this result using a particular kind of study called a data bank study. Now you think, well, what could be the cause of these big increases? Confounders? You know what confounders is? If you're looking at lung cancers and you've got people who smoke and also work in a uranium mine, the smoking confounds for the uranium mining exposure, okay? Or it could just be sheer coincidence, a fluke. Or it could be, they're called population mixing theories. Could be, well, there are chemicals from nuclear power stations as well. Exposure to viruses, fungi. No, we looked at all of those, and in fact, the people who did the KIC study looked at all these, and there was nothing. It left radiation or radioactivity. But KIC said that the radiation doses were too low, but they actually didn't have any dose estimates, and there's a reason for it. And that is, I'll just go on to the next one. There were big uncertainties in the estimated doses and risks near reactors. And this is not just me saying this. This is the official report of a government commission, the Cherry report in 2004, funded by the UK government. Why are there large dose uncertainties? Well, basically, you have to have at least 4 models. And they're listed there, the environmental models, biokinetic ones, dosimetric ones, and dose weighting factors. Now, all of them, what you do is you get one figure from the environmental model, and you plug it into the second one, you plug it into the third one, you plug it into the fourth one. Each one of these models, all of these models, have uncertainties, which are not taken into account. The reason being is this, is that for each one of these models, you'll get a range of results, okay? Because that's what happens. You're playing with figures, and you'll have a range of results like I've shown here. What they hope is that you'll have the dotted figure. Nice, sharp peak. And you can use the peak figure there to plug into the next model down the line. But it's not like that. What actually happens in reality is a solid line. You have a wide range of results. And what they do is they pick the central figure, but the fingers crossed type thing, you know. And in other words, it could be way up high, where the 95% cutoff is, or way low, 95 or 5%. Now, just to give you an example of what I'm talking about here, let me go back. When I say uncertainty, you'll say, well, what do you mean by uncertainty, Ian? And it's this. It's the ratio of the 95 percentile to the 5 percentile, right? So if you have a very wide range like that, you divide the figure from 5 into 95, and you get a bigger number, all right? So that is an expression of how uncertain something is. Right. This is, do you remember I said to you biokinetic models? Here's an example from one of these models, biokinetic. If you take, say, cesium and you use the ingestion route and you look at the doses to red bone marrow, you get an uncertainty range of 4. Hey, that's okay. We can deal with that. But if anywhere else, say, for example, plutonium down here at the bottom, using ingestion, and you've taken the dose to the bone surface, you get a range of 20,000. Now, what does that mean in practice? It means that we don't know, and it's better not to use these figures. And that's exactly what happens. We've got, and I just picked as one of the bottom, but there are large uncertainty factors for many of these radionuclides, okay? Take my word for it. These dose estimates that are produced by nuclear power companies or by regulators aren't worth the paper they're written on. They are guesses. They contain huge uncertainties which are unquantified. So when a nuclear power company says, no, but these risks that we're finding cannot be done, you know, can't be, our doses are far, far too low, their doses are not measured, they're estimates. And these estimates are way off. And it's not just me saying that, it's the UK government saying that. Now, that's all about doses. I'm going to talk now about risks, which is different from dose. For risks, you also have to use models. And the current model that we use is the lifespan study, which is used by ICRP based on the 1945 Japanese bomb survivors. But I'm going to cut down this very shortly and say that there are big, big uncertainties with that as well. And in fact, it's really inappropriate to use that as a risk model. Why? Because the exposures there came from a bomb blast, and the bomb blast lasted 0.1 of a second, something like that. And it was exposure to neutrons and gamma rays mainly. Yeah. But what we are measuring when we're near nuclear power stations is internal emission, not external, which lasts for years because it comes inside you, to beta emitters, which is or alpha emitters, which is nothing to do with the Japanese risks, okay? So take-home message, we're applying the wrong risk model here. And I'm cutting it down short. So basically what I'm saying is that the radiation exposures in the nuclear power stations could be a cause. I wrote an article in the Journal of, if you can make it out, of Environmental Radioactivity, which was published last year. And the Journal of Environmental, let me tell you, the Journal of Environmental Radioactivity is a very small journal. There aren't many people who have that in the top of their magazine lists. And I was astonished to find out, and so were the editors, that this article has been downloaded coming up to 2,000 times. That means 2,000 people around the world forked out about $36 each to download this. Now, apart from the fact that the publishers now are making a lot of money out of this, I don't get a penny for that. But I'm being ironic. I'm very pleased, in fact, that so many people have downloaded it, because the only people who are downloading it are radiation scientists and nuclear scientists. And they're getting the message. And to me, that's the most important thing. Now, in this article, I set out a hypothesis to explain why there are so many childhood leukemias near nuclear power stations. And it's this, that when you open up a nuclear reactor to take the old fuel out and put the new fuel in, about once a year or so, you have big spikes in the radiation gases which are inside the reactor. These result in high concentrations in the pregnant women who are living nearby. You have large doses to embryos and fetuses, and the babies which are born are pre-leukemic, and after a couple of years, they develop full-blown leukemias. That's my hypothesis. Why do I think that is? Because Professor Rusig in Germany, she independently, she theorized that the bone marrow stem cells, this is in leukemias, in embryos and fetuses, receive a first hit of radiation. You get a pre-leukemic clone. The dotted line is where birth occurs. And then after birth, you have a second hit, and then you have a full-blown leukemia cell. And this is, by the way, this is now fairly well accepted. So we're talking about when the reactor's open, you have a big spike of radioactive gases. What are the gases? H3, which is tritium, which is the radioactive form of hydrogen, carbon-14, and krypton-85, and some other noble gases. It's like this. This is the first time that this has actually been shown, because nuclear power companies have kept this well hidden that there are spikes. When it was released in Germany in 2012, it was the first time that anybody knew anywhere that these spikes occurred. And I'll tell you how we got this data in a second. It's quite interesting. But show you here. Down at the bottom here, this is 3 becquerels per cubic meter here. This is throughout the year 3 goes along. And down the other way it goes 3 down along, okay? But when they open up the reactor, it jumps up to 1,500 or so. And it was 500 times higher. And it's that big pulse of concentration which goes out, which labels the cells in pregnant women. That's the important thing, the big high concentration. And how I was, in fact, what happened, it was me who asked the Germans, IPPNW, who have a very, very powerful anti-nuclear movement in Germany, if they try and get this data, because I had shown them this. This is quarterly. So, like 4, 4, 4, 4, 4, 4, 4. So every year, right, you had this big spike. And I thought, hey, that's a refueling spike. And they agreed with me, and so they, I don't know how to get this back. I'm totally lost. I don't know how to get this. This one here?
Yeah.
No, it's not. Oh, yes, it is. Ah, good. There you go. Sorry. Technology failure. This data here, what I wanted to show. How we got this. This comes from the German power plant of Gundremmingen in Bavaria, in Germany. And what happened was that in 2010, this is an interesting story, the German Länder government was elected, and it was a red-green government. Do you know what I mean by red-green? It means the socialists and the green parties together formed a government for the first time in German history. that this particular state, Bavaria, had elected such a government. And what they did was that many of the anti-nuclear people were thrilled to bits because the Environment Ministry was a Green, a wonderful woman, Karen Busher. And she went to the nuclear regulatory and said, I want hourly data for when the nuclear reactors are opened up. And they said, no, you can't have it. And she said, what do you mean you can't have it? She said, it doesn't exist. And she said, well, we've got whistleblowers that tell us it does exist. I'm not giving it to you. Yes, if you don't give it to me, I will cause a fuss. So what? We don't care. This went on, by the way, for months. I'm cutting together a short story. And then finally she said, I want your resignation, undated resignation letter on my desk on Monday morning. What? You can't do this. Yes, I can. She got it, and there was a undated resignation letter. She said, I'm going to put the date on this and tomorrow, unless you get the data is on my desk. She got the data. And this is it. And when we saw this, bingo, we knew we'd hit it. It's these spikes. Now you may say, well, hang on, Ian, why hasn't it, we should have known about this. Yes, we should have. But since the dawn of the nuclear age, say 1955, 56, nobody has ever discussed this. Nobody. But the nuclear power companies and the regulator, they all knew about this, but we're keeping it quiet. But to me, this is a smoking gun. Fine, okay. Okay, I'll have to go through this quickly. Now, to give you a visual image of this, this is a power station in Romania. It doesn't run a map. This is actually the Danube River in Chernavoda. But this is what a visualization of what happens when they open up the reactor. You get a big plume of radioactive gases, right? And that's if the wind is strong. If the wind isn't strong, you get this. And the redder it is, the more doses there is, okay? Did you make these? No, this is actually from, it'll tell you, these are all available, and you can pick them up, and you can read them. This is from the 8th meeting of the IAEA MRAS Tritium C14 Working Group in 2007, okay? This is all official. This is official stuff. And the reason why I show it to you is not because of the numbers, but to show you a visual idea of what happens when they open up the reactor, okay? You get these plumes. What are they? As I say, they're tritium and noble gases. And you may say, yeah, Ian, so what? And that doesn't mean there's really tritium in the air. Yes, there is. This is hard data showing tritium concentrations. The closer you get, the higher the levels, okay? And then you get the people who say, whoa, come on. Just because you've got tritium in there doesn't mean there's tritium in food. Well, yes, there is. And here's the data. The closer you get to the reactor, the higher the tritium concentrations in food and vegetation, soil, meats, milk, eggs, fruits, cereal. Okay? This is all official data, by the way. What is tritium? It's the radioactive form of hydrogen. I'm going to have to run on this. We can't hear it, feel it, smell it, or anything. But tritium is really unusual. It gets everywhere because it's radioactive water. And when it gets inside you, it sticks inside you. Here's a list of hazardous properties of all radionuclides, okay? There's about 12 of them there. We should really have a system of hazardous radionuclides. But tritium ticks almost all of them. All right? So in other words, tritium is really quite serious. We should be applying the precautionary principle. And these are my recommendations. But I want to say something else. This is a good way of visualizing what happens near with information and science in the nuclear area. Many of you who are scientists will have heard about the space-time continuum and how gravity affects it. Basically, gravity warps the time-space continuum like this, just like this warp here, like a rubber blanket, which you put a big steel ball on it, and you get this warping of information and intelligence, right? And that's what happened with nuclear power. You have this warping of intelligence. Right?
Yeah, we really have to stop. Everybody's coming in. It's fascinating. The slides will be on the side, all the slides. I'm sorry to stop you because everybody wants to come in. I guess if you have questions, we'll have to ask them outside because thank you very, very much.